Yeah, so good evening, everyone. Welcome to the uh, problem solving session of week number 3 for computational complexity theory course on NPTEL. Again, my name is Bhavya Deeprai, uh, and I'll be holding these weekly tutorials, which will also be uploaded in YouTube. Again, the recordings will be available, but we of course encourage joining online so that there is more interactions also. So okay, let's go to the point. So now that the deadline, okay, for assignment 1 and 2 deadlines are over. So what I'll do is I'll discuss some answers with you. Okay, the and we will do some assignment discussions for 1 and 2. And I won't do them for all the questions. I'll do them for a selected few which are more on the difficult side, where more concept is required, or you need to be more careful. Okay, or overall difficulty is very high. Then I'll be discussing those questions, and so I've selected them, and then I'll discuss it now. And after the discussion, we'll go into this week's topics. Getting it? So that's what we'll do. And also, if while discussing the assignment questions, if you think that there are other questions that deserve a discussion, then please let me know. We'll swiftly discuss it. Okay. So let's get into business. Okay. So here are the questions from assignment 1, which were more on the difficult side. Okay. So suppose there is a language L in NP that is not NP complete, and L is not equal to phi, and L is not equal to sigma. Which of the following statements can be inferred from this? Okay. So let me repeat it. Let me show it to you. So we already have P, the set of polynomial time decidable languages, right? Now, and next we have NP, which contains P, the set of all non-deterministic polynomial time decidable languages. Okay. Now we are saying, okay, and this is contained in sigma star, the set of all languages. Now we are saying, there is, and we know that there is a particular class of problems called NP complete problems. Now NP complete problems could be like this, or NP complete problems could be like this, right? Maybe there are problems in P which are also NP complete. If it is shown that there is, if this intersection is there between P and NP complete, then you show that P is equal to NP, right? That is the first takeaway. Another thing that we don't know is whether NP is equal to NP complete, whether all the problems in NP are NP complete. Okay. Now let's say, suppose P is not equal to NP, then question is there a language here which is not NP complete? Okay, something along those lines we can ask a question. And is P NP equal to NP complete? This kind of question we can do. And but here what they are saying is, let's say there is a language L in NP. Okay, L is in NP. It is either here or here. Okay, and or here it is NP complete. But what they are saying that it is not NP complete. We have come up with a language which we can for sure say that it is not NP complete. It is here. Okay, it is not here. We have come up with a language L which is for sure not NP complete. I'll write it in a slanted way so that we don't. Okay, and next thing is L is equal to phi. L is not equal to phi, and L is not equal to sigma star. Yeah, sorry, this is not sigma star. This should be the power set of sigma star. That is the set of all languages. Okay, which of the following can be inferred from this? That is the question. Firstly, okay, the main point to observe here, okay, is that is the following. Any language in P, any two languages in P, say L1 and L2, reduce to each other in polynomial time. This is the main observation. Any two languages reduce to each other in polynomial time. Mathematically, if I have L1 and L2, which is in P, which belongs to P, okay, then L1 reduces to L2 in polynomial time, and L2 reduces to L1 in polynomial time. Any idea why?
Yes, because if L1 is getting reduced to L2, then the problem L2 is at least as hard as the problem L1 is. And so the thing is that since both can be solved in the polynomial time,
okay,
so clearly there exists a transformation function because the complement because there exists a transformation function which can convert every instance of a problem into an instance of that problem.
Yeah, but can you specifically tell why am I able to transform it?
Just because, say, if I add anything into the polynomial, or if I apply a polynomial function over a polynomial, the result would again be a polynomial.
Right.
So maybe because of this.
Yeah, that is close. Okay, that is close. Right. The key idea is here that since the reduction is polynomial, okay, and yeah, I'll build on that. That is close. So so here is the proof for this. Okay, give me any two languages in P. Any two languages in P. You just give me those two languages. I'll show you a reduction from one language to another. Okay, so okay, yeah, I'll show you a reduction from one language to another. Okay, and how do I do it? I need to take the machine for L1. I need to design a machine for L1, and using a machine for L2, use L2 as a subroutine, and give a reduction sigma. Okay, and that particular x will be transformed into sigma x, and if this guy says yes, I'll give yes, and if this guy says no, I'll give no. Okay, so here is what you do. Okay, here is what you do. So description of machine, Turing machine, M1. Okay, this decides L1. Okay, and on input x. Okay, now what do I do? Okay, wait, I'll just show you the reduction. Both are in P. So let's say L1, let L1 and L2 be in P, and both of them are P via Turing machines M1 and M2. These are polytime Turing machine and deterministic. Okay, Both the machines run in deterministic polynomial time because L1 and L2 are in P. Now here is the simple reduction. Okay, here is the reduction. Okay, and so what I'll do is, okay, first I'll do is run, okay, M1 on X. Okay, and separately what I'll do is let me call it something. Let W be a string such that W is in L2. Okay, let's say I call it W1, W2. Take two strings. One is in L2, the other is not in L2. Okay, one is there in L2, the other is not in L2. Okay, now what I do is I run M on X, and M1 is able to tell me whether X is in the language L1 or not. Correct. Once I run M1 on X, if M1 accepts, okay, what I'll do is run W1 on L2 on M2, and when I do this, M2 will obviously accept. Because why? Because W1 is a string that belongs to L2. Okay, I already know it before I let's say. That's why. Okay, and these are fixed. Okay, these are constants. Okay, these are fixed, W and W2, W and W2. And if M2 accepts, rejects, if M1 rejects, then run W2 on M2, and here M2 obviously rejects. So here I gave a reduction such that whenever M1 accepts, M2 also accepts. Whenever M1 rejects, M2 also rejects. So M1 and M2, okay, and this runs in polynomial time, and so does each of these. All of these run in polynomial time. So therefore, this is a reduction from L1 to L2. Is it not? This implies L1 polynomial time when you want to reduce this to L2. So we are
W1 and W2 here.
Yeah. Goel, can you say it again?
Yeah. So what are W1 and W2 here?
What are W1 and W2? Okay. Right. What is W1 and W2? So let L2 be some language. L2 is any language, right? Some language in P. And W1 and W2 are just two constants that I identified such that W2 is outside L2 and W1 is inside L2. Okay, these are constants. I've fixed it already. So this is hard coded into my machine's description. So I don't need to worry about finding W1 and W2. W1 and W2 are guaranteed for me. Okay. Getting it? Okay. So yeah.
But how does logic work then? That when L1 accepts, when M1 accepts L1, W1 is coming into the picture, and when L1 rejects, so then we think of W2 vice.
Right. Okay. Now I'll tell. Yeah. Right. So when an L1 accepts, okay, when X belongs to L1, then sigma of X, okay, belongs to L2. Okay, and X does not belong to L1, then sigma of x does not belong to L2. Why? Because sigma of x is defined to be W1, okay, whenever x is in L1, and W2 whenever x is not in L1. Getting it? This is what we did essentially, where W1 is in L1 and W2 is not L2. Sorry. So I'm forcing this reduction to happen. Getting it? So actually what we are doing is we are not running the machine for L2 at all. Sorry, we are not using any answer of L2 at all. Actually, getting it? We are not actually using the answer of L2 because see, the transformation we make may arbitrarily say yes or no, right? We cannot easily fix it. But now what is happening is whenever M2 says yes, I'm saying yes. Okay. Oh, sorry. Okay. If run M1, then accept. M1 accepts, and here M2 accepts. Okay. M1 accepts. Sorry. In here M1 accepts, and here M1 rejects. Sorry. Is this clear?
So the point is that when M1 rejects, so then there could be some other constant, say W3, and that quite possible that which may result into the acceptance.
Yeah.
My point here is that okay, so is it always possible that a problem which is solvable in the polynomial time and its instance always be rephrased as an instance to some other problem? Like say if we take an example of all pair shortest path solvable in the polynomial time, and say if I take an instance of getting the minimum spanning tree again solvable in the polynomial time.
Right.
Now how can I prove that the all pair, each and every instance of the all pair shortest path can be rephrased into an instance of minimum spanning tree?
Yeah. You're right. So this is what we are doing. Okay, we are not actually rephrasing it here. Okay, we are just misusing the definition of reduction. Okay, so what were the two languages you talked about? One was MS.
Yeah, first one was the all pair shortest path problem.
Shortest path problem.
All pair shortest path. So that is we use the Flood-Warshall algorithm to solve that problem.
Right.
In the effort of order of n cubed.
Well, see, all pair shortest path is these are not decision problems. Can you give a decision problem? Say checking whether a path from S to T is shortest or not. Okay, wait. Oh yeah, that using Dijkstra's you can verify it, right? Whether it is the shortest or not. Okay, so I'll call it short path. Okay, given G and a path P, check if P is shortest path. Fine. This problem is in P because what I can do is I can run a Dijkstra's algorithm, and then in polynomial time it will terminate, right? It runs in, I think, cubic time, and cubic or quadratic, I forgot, but it runs in polynomial time, and then what you can do is you can check if it is the shortest. You can check the length of the shortest path and then check whether the given P is actually also of that particular length. Okay, and let's look at another simple problem. Let's do linear search. Okay, given an array, right, A, and given an array A and another call it Y, check if Y belongs to A. This is a linear search problem or search problem, right? So you can use either linear search or binary search to solve both of these, right? Hello? Hello?
Yes.
Yeah,
Yes.
yeah. Okay, good. Okay. Now, observation is that both search path, a short path, and search are in P. This you can clearly see, I think. The first one apply Dijkstra's algorithm. The second apply um, uh, uh, apply linear search or binary search, whatever, and call it algorithm 1 and algorithm 2. Okay, via algorithm 1 and algorithm 2. Okay. Now, what is the W1 and W2 here? Okay, okay, so to show short path reduces to search in polynomial time minimum. This is what we claim. Now, yeah. Now, I'm saying choose a W1 such that, oh god, sorry, this should be L2. Sorry. Okay. Now choose W1 such that, oh no, okay. What am I doing? X belongs to L1. That is correct. And if W1 belongs to L2, W2 does not belong to L2. You need to choose. Okay, what is L2 here? What is the L2 in this case? L2 is search. L1 is shortest path. Short path. Now, we need to give an example of a string which is in search, that is L2, but not in another string which is not in search. Okay, so here W1. What is W1? W1, fix anything. Fix any pair, any suppose 1, 7, 5. This is the first set where you need to find whether 5 is there. This is in search. Now fix W to be anything, say 1, 2, 7, where you need to search whether 4 is there. This is not in search. Why? Because 4 does not belong to the set. Getting it? So what I'm what I'm saying is, when developing the reduction, we do not need to come up with an algorithm to check whether to find two places where it belongs to the L2 and it does not belong to L2. Just fix it. Fix the algorithm. Existence is enough. Existence of these two strings are enough. Getting it? Now,
Yes.
right. Now the reduction is as follows. Run algorithm 1 on input, whatever that shortest path input was, G, and G and P is the path given to you. And if algorithm 1 says yes, what I do is I actually cheat with the definition of the reduction. I'll just give W1 to run W1 on, okay, run algorithm 2, which solves the search problem on W1. And algorithm 2, since 5 belongs to this, it belongs to search, that is, we'll say yes, says yes. and say something like, if algorithm 2 says yes, then output yes. Similarly, if algorithm 1 says no, then what do? Run algorithm 2 on W, okay, and say no. Because algorithm 2 on W will clearly say no. Is this clear?
Yes, so I was thinking that what if we replace shortest path by some NP-complete problem, uh, say by click,
If if
then
if
will the
yeah.
same logic work? Or
No. Why? Because um, running algorithm 1 on input. Now this is not clear because we don't have an algorithm that we don't know whether we have an algorithm which runs in polynomial time. This necessarily needs to be done in polynomial time. Okay.
yes,
Okay. So that's why this
yes.
will not fit into NP. So we cannot say something like all NP language reduce to each other in polynomial time. Getting it? Suraj, are
Yes,
you?
but I have,
Is that fine?
yeah, but I,
Yeah. Continue.
yeah, but I have a related issue here that since we are carrying out a reduction, that I
Hmm.
mean, the machine which is carrying out the reduction
Right.
should be
Should we?
less powerful than the machine which is actually solving the problem, or we assume that the problems again should be less powerful than the machines which are supposed to solve the problems. Like say if L1 is getting reduced to the problem L2,
Hmm.
so then the machine which is
Then
carrying
the
out the transformation should be maybe less powerful than the machines which are supposed to solve L1 and then L2. Like the way we work with the NP-complete problems. Say if L1 is the element of NP and L2 is the element of L1 is the element of NPC,
hmm.
and L2 we want to prove is NP-complete. So
Hmm.
then the machine which would solve the two NP-complete problems would be more powerful, or is assumed to be more powerful than the machine which is carrying out the transformation from L1 to L2. And now in this case, what is happening that the machine which is solving the shortest path is also a DTM kind of the thing. The machine which is solving the search problem is also a DTM,
Hmm.
and the machine which is carrying out the transformation is also a DTM.
Hmm.
So for this transformation, either we use something which is less powerful than P, something like say the class L, or I don't know whether NL is there in is within the P or not, but certainly this L class is there as a subset of the class P. So
Right.
this transformation then should be carried out in the long space rather.
Yeah. I'll come to that. I'll come to that. Good question. Okay. I think I got your question.
Okay, okay,
I think I got your question. I'll come to that. Okay. Okay.
okay.
Okay. Okay. Um. So yeah. Where was I? Okay. So this is clear now, right? Any two P languages will reduce to each other in polynomial time. And I'll come to this. I'll come to this. You talk about why if we relax it, if we restrict it to L, then why is it? What happens, and so on. I'll come to that. And but this is the gist of it. Now, there is one problem with this. I will not be always able to. Okay, first of all, is it clear? Suraj, is it clear? Hello, Suraj, is it clear? Are you able to hear me? Okay. Okay. Maybe he's gone for a while. Okay, let's continue. Okay, so this is the first part. Now you are convinced that okay, they reduce each other, but there is one problem with this. I should not be able to do it every time. What are the cases when this reduction is not possible? Any idea? Look at it.
So yeah, like say if you consider the extreme cases, like say phi or cleaning closure of sigma kind of a thing, wherein every time we will either get the answer as no or the answer is yes.
When 5.
So when L1 is either a phi or
Okay.
the cleaning closure of sigma. So if
L.
we have a situation wherein the answer is certain, either the every time the answer is going to be a no or the answer is going to be a yes.
Right. Right. Good. Yeah. That's right. The problem is we may not always be able to obtain suitable W1 and W2. That is, W1 is in L and W2 is not in L2. This is the problem. We need a W1 which is in L and we need a W2 which is outside L. What if that does not happen? And can you tell me a case when this does not happen? What should L be? L2. That is, yeah, I think you already said it. That is, suppose L2 is equal to sigma star, then everything is in L2. I cannot ever give a string to you which is not in L2. So this means W2 cannot be found, does not exist. Right? And if L2 is equal to empty, then W1 does not exist. I want a string which belongs to L2. But since it is empty, I cannot give you a suitable W1. Right? So this reduction does not work for two kinds of. Am I not clearly audible? Some audio issue. Oh, okay. Yeah, I cannot hear you. Well, I mean, are you trying to speak? Yeah. Okay.
No,
Now
no.
you can. Yeah. Continue.
It is my whether I am not clearly audible or what.
Oh, no, now you are audible. But
Is my audio is my voice audible to you or is
now you are audible, I think. Yeah.
okay?
Okay. Okay. So is it clear so far?
Yes, it is clear.
Okay. So when it is L2 is either sigma star or L2 is phi, then this is not true. Okay. I cannot use this reduction. So what does it mean? What does it mean? Now my claim is changed. Okay. My claim is changed. New theorem. The previous theorem was flawed. It is that for all L1 and L2 in P such that, okay, L1 is, what did they say? Okay, I'll only talk. Okay, L1, L2, in our case L2, is not equal to sigma star or phi, then L1 reduces to L2. Getting it? And now, according to question, L2 is a language, or L, they have called it L, I'll call it L2. L2 is a language which is not NP complete. We know for certain it is not NP complete. Then first consequence, what is the first consequence? P is not equal to NP. because of this by theorem. I'll call it new theorem 1. Why? Because if P is equal to NP, okay, then L2 will be in P, and by theorem 1, what will happen? For all L1 in P, which is nothing but NP, L1, because that's by assumption, right? For all, that's by assumption. This equal to looks like 2, so I'll remove it. Okay, yeah, right. For all P, which is equal to NP, L1 reduces to L2, which implies L2 is P complete, or that is NP complete, because P equals NP, under polynomial type reductions. Getting it?
Actually, this argument is not that clear. Can you show the problem statement again so that we can understand? So, yeah, so L is the element of NP, and that is not NP complete, and L is neither phi nor the Kleene closure of sigma. Yes.
Getting it? Because these two conditions are satisfied.
Yes.
We have that for all L, let me call it L1, okay. L1 will reduce to this particular layer that they have in the question, which I'm calling it L2. Okay.
Yes. So what is L1 here? That for all L1. This
sorry, I forgot to quantify it. For all L1 in NP.
Okay. Now I understood. Yeah. So for all L1 in NP, then this would be possible. But then, okay. But this is not the case. Okay. Yes.
Right.
So this L1 is the element of P.
L1 is an element of P. Yeah.
P. Yeah.
Okay.
So if for all L1 is the element of P, then there is no point in reducing this to the NP problem. Why are we doing this?
What?
I mean, what about this logic? And I mean, why to move in this direction? It is true. So what till now we have only shown one thing, that every problem which is in P can be reduced to any other problem which is in P
in polynomial time.
Unless in polynomial time, unless the problem is either phi or the Kleene closure of sigma.
Right.
So how does this relate to this problem statement? This question number 1's problem.
Right. Now why? Because now they are saying so many options. P equals NP, P is strictly contained NP, P is not equal to NP. First I'm claiming P is not equal to NP. Okay, I've written it here. First I'm claiming it P is not equal to NP. If this happens. Because I'm now doing proof by contradiction. I'll assume the opposite. Let's say P is equal to NP. Let's say P is equal to NP. Then what does it have? What does it mean? Since my L2 is NP complete, it means it's an NP also. So L2 is in P because P equals NP. First thing.
L2 is not NP complete. L2 is merely in NP.
L2 is?
L2 is not NP complete. It is merely in NP. L2 is the problem.
Right.
Which is only in NP, and it is not NP complete.
Yeah. Sorry. L2, sorry. Okay, L2 is in P, not NP complete. Right.
Yeah.
Okay. So L2 is in P. L2 is in NP, and P is equal to NP, so L2 is in P.
Yes.
Now by theorem 1, everything in P reduces to each other. So everything in P reduces to L2 also.
Yes.
And P is equal to NP. So everything in NP also reduces to L2.
Yes.
Right. So L2 becomes NP complete. But what did we assume? L2 is not NP complete. That is what we already know. which is a contradiction.
Yes, but if P is equal to NP, then as you wrote here, that L2 could be P complete also.
Yeah. But
So,
we are
but then
saying
it
P
is.
and NP are the same. No, P and NP are the same. That is our assumption for the proof. So if
Oh,
L2 is
yes,
P complete, it is NP complete also.
yes, yes. Now I understood.
Okay, I'll write here again because P is equal to NP.
Yes, yes, yes.
Okay. So that shows P is not equal to NP, and so if P is not equal to NP, then what does it mean? NP is not contained. NP is contained in P cannot be true,
Yes,
and it also means that P is strictly contained in NP because P is
yes,
contained in NP and they are not same. Okay,
yes,
this is the first
yes.
question. Okay, okay, good. Now let's quickly
Yes.
look at another. Yeah.
I have a slightly related question here.
Hmm.
So, like the satisfiability or the 3CNF satisfiability is the representative problem, representative NP complete problem,
Hmm.
and which was first proved as NP complete.
Hmm. Hmm.
So
Hmm.
now, which representative problem is there in the P complete complexity class?
Okay, good. Okay. For NP, we have something called satisfiability. Okay, this is not the only non NP complete problem, but this exactly represents what NP is. Okay,
Yeah.
and then you have L. For L, we have path. Okay, as called in the lecture. Sometimes it is also called reachability problem.
Yes.
Okay, for P, there is a problem called CVP, which is called the circuit value problem. And circuit value problem is defined as phi comma p such that phi evaluates okay sorry uh, phi on phi is a circuit, okay, and phi is a circuit on a1, not a1, x1, x2 and so on till xn, and you are also given an assignment a1, a2 and so on till an, okay, and you are also given a bit, okay, so that phi on a1, a2 and so on evaluates to b. In other words, circuit value problem simply asks, given a circuit and an assignment, does it evaluate to 1 or not? Getting
Okay.
it?
Okay. Yeah.
So these problems that are representational are what are called canonically complete problems for the class. SAT exactly represent what NP's machine is doing by Cook-Levin reduction, and P and CVP you can try it with using same thing, Cook-Levin reduction. Try to check it out, okay. And what the log space machine is doing, okay, not L, sorry, NL. What NL machine is doing is exactly what directed reachability is doing. And for L also there is a language called ureach, okay, which is undirected reachability, okay. And this is not exactly canonically complete, but nowadays it's assumed that it is canonically complete for L, okay. But yeah, so CVP, the circuit value problem, is an example of a P complete problem, but there are several P complete problems, okay. And there's a problem called Horn-SAT, which is also quite famous. Yeah.
Yeah. Thanks.
Now coming to your previous question, why is it so? What are reductions? Okay, reduction is a tool two separate classes or join classes. Okay, it shows one language is harder than the other and so on, but we saw that for P, polynomial time reduction is not sufficient to distinguish. It is sufficient for NP, polynomial time reduction, but it is not sufficient to distinguish languages within P. So that is what you were saying, right? What about this? So how do we distinguish languages in P? We need to use a weaker reduction, or actually a stronger reduction that way. So we need to work with something like say LM, log space reductions. So now if you ask the question whether are all P languages reducible to each other under log space reductions, that is not clear. We do not know.
Yes, yes. Probably then the problem will become interesting, because then there would be some problems which are there in P and are not reducible to the other problems which are there in P in the logarithmic space.
Right. So to for two classes, if one is much more harder than the other, if one class is very big, to distinguish we can use a weaker reduction, but or stronger, however you want to see it. But the strength of the reduction actually dictates whether you can distinguish the class or not. That's right.
Yeah.
Okay, good. So for example, if you want to show, say if path this let's say path reduces to 2 sat, okay, and both are in L. 2 sat, both are in L. You cannot use P. You cannot use P, polynomial time reduction. Why? Because this is obvious, because both of them are in P, and you obviously they reduce to each other in polynomial. A more interesting result is that path reduces to 2 sat in log space polynomial reduction. That's why L complete languages, NL complete languages are talked about. Okay. I mean, NL complete languages have log space reduction instead of polynomial time reductions, because NL is contained in P. Yeah.
Yeah. Is path an element of L or NL?
Please, what?
Is path problem an element of L or NL?
The path is in NL. In fact, if you show that path is in L, then it's over for us. L equals NL.
Yes,
Right?
because then here I have written this 2 sat.
Okay. Sorry, you mean here I've written L, right? Okay.
Yes.
Right. Sorry. Okay. Okay. So let's look at this question. Okay. Consider the below two problems. Short path G is an undirected graph. K is at least 0, and there is a path from S to T of length at least K. And long path is G, S, T, K. G is an undirected graph. K is at least 0. And there is a path from S to T of length at least K. This is at most K. The upper one is at most K. And long path is at least K. Okay. And the question is both are in P, both are not known to be in P, one is in P, other is not in P, and so on and so forth. So the answer, okay, the first answer is that short path is in P. Any reason? Can you give a polynomial time algorithm for this?
Yes, there are many. Dijkstra's algorithm is there, Bellman-Ford is there,
Right.
even the Ford-Warshall is there.
Right. So let's use Dijkstra's algorithm. Okay. Use Dijkstra's algorithm on graph G, and get shortest path from S to T, right? Once I get the shortest path from S to T, okay, say call the path P, okay, and check if length of the path is at most K, and done. Output yes or else output clear. So short part is
Yes.
so the other way around. Any idea?
So for the longest path,
Hello, hello, yeah.
I don't know. Yeah, I don't know exact reason, but probably for the longest path, if I try to find the longest path, then I'll have a liberty to make a move to the same vertex multiple times. And if I make a move to the same vertex multiple times, and I mean, then every time I would be increasing the length of the path. So therefore, getting the longest path it would be a difficult problem. So longest path is not there in B.
Okay, yeah. But whenever we say something does not, okay, answering a no is more difficult than answering a yes. So what you said was an evidence that probably it is not in P, but it is not not an evidence. It is a intuition that it is not in P, but it is not an evidence, right?
Yes.
We cannot say for sure, right? But we can thankfully say for sure using reductions, okay, that it is not known to be in P or not. Okay. How? Okay, claim 2 is that if long path is in P, okay, then P is equal to NP. Okay. How? If first of all Hamiltonian path, Ham path reduces to the longest path problem. I'll call it the longest path problem. Don't confuse it with the long path problem, okay? And longest path problem is in P if long path is in P. Okay?
So what this long path problem is?
Right.
Long.
So longest path. What we were talking about was a long path. Long path is there is a path from S to T of length at least K. Longest path is given G and K, longest path between any two vertices is K, exactly equal to K. Getting it? If I have a graph G and there are vertices, I take any longest path. Okay, let's say this is the longest path, and this is of length K. That is the longest path possible. Now, what did I say? Claim is that Hamiltonian Ham path reduces to longest. Any idea how? Longest path says it is the task of checking whether G has longest path between any two vertices is K.
Longest path is K. So we can have the longest path when only when we visit every vertex. We have visited every vertex exactly once, and
No,
we have
the other way around. The way of phrasing is the other way around.
okay. Okay. So if we find if we traverse every vertex exactly once,
Huh?
then quite possible that I may get a long path. And if I do not traverse every vertex exactly once, then I may end up with a path, and that may be the shorter one.
Okay, good. And what is a Hamiltonian path? It visits all the vertices, like you said. And
Uh,
right, if there are n vertices, then what is the length of the Hamiltonian path? If for a path which visits all the vertices.
okay, so if there are n number of the vertices, and then so the length of the path would be yeah, so n minus one.
Exactly. So if I have any graph G has a Hamiltonian path, or G belongs to a Hamiltonian path if and only if, okay, G has the longest path of length n minus 1. Correct?
Yes.
Right. And if, okay, let's say I only argue in this direction, obviously, okay, so why? Okay, I'll write the correctness also. Why? Because if G has Hamiltonian path, then there exists a path P visiting all n vertices, and length of P is equal to n minus 1. The other way around, if there exists a path of length n minus 1 in G, then since the vertices are not repeating in a path, okay, then say P, then P is a Hamiltonian path. Okay, so what does this mean? Hamiltonian path reduces to longest path. This is clear?
Yes.
Nice. Okay, good. Now my claim 2, I had two claims, right? Yeah. Claim 1 is short path is in P. Claim 2 is if long path is in P, then P is equal to NP. And how? Because ham path, many one reduces to long. Actually, this is not correct. Okay, so yeah, this is correct. Ham path, this we've shown. And longest path is in P if long path is in P. This is my actual claim 2. So can you summarize this ham and long path reduction in short? Sure, I'll do that. Sure. Okay, Suraj, what is ham path? Ham path is all the graphs, the set of all graphs which has a Hamiltonian path. What is a Hamiltonian path? It is a path. Okay, it is a path which visits uh, all the vertices in the graph. Okay, for example, this has a Hamiltonian path as follows. This is an example of a Hamiltonian path. Therefore, this graph belongs to ham path. And what is long path? Okay, long path has two inputs. One is the graph itself and a k value k. Okay, and and say this is the graph, and let's say k, this is g, and let's say k equals 3. Okay, k equals 3, this is g. Okay, if k equals 3, I'm asking you what is the longest path in this graph. What is the longest path between any two vertices? And well, this is of length 3, this is of length 3, and yeah, right, 5, this one, right, this is the longest path. So g3 is not a good because the longest path is greater than 3. So g comma 3, if g is this particular graph, does not belong to long path. Oh, sorry, not long path. Really sorry, we are getting confused with long and longest. This is the longest part problem. Does not belong to longest path. And g4 similarly also does not belong to longest path. G comma 5 belongs to longest path. So this is clear, right? The definition of the problems. Right? This is clear. Okay. Okay. So now claim, my claim 1 is, okay, that okay, sorry, not claim 1, claim 2.1, Hamiltonian path reduces to, okay, I'll call it claim 2.1, Hamiltonian path reduces to longest path. This is my first claim. Okay, Hamiltonian path reduces to longest path. And how does it reduce? This is my answer. G has a Hamiltonian path if and only if G has the longest path of G is of length n minus 1. This is the way to read it. Correct. Now here's the question. Okay, Suraj, if I have n vertices in my graph, okay, if I have a graph and there are n vertices here, v1, v2, and so on, so forth till vn, and I have a path that visits all these vertices, what should be the length of the path? Number of edges in the path? N minus 1 edges, correct. And this graph, okay, sorry, this graph has n vertices, and we are also saying that this, let's suppose G has a Hamiltonian path, which means it has a path which visits all the n vertices, and therefore the longest path has n minus 1 edges. So this is true. First direction is true. First direction is true. Now we need to prove the second direction. Second direction is the other way around. Let's say there exists a path of length n minus 1. There exists a path of length n minus 1. And okay, there exists a path of length n minus 1. Okay. And I'm not, remember, this is a path. I'm not allowed to repeat the vertices. I'm not allowed to repeat the vertices. Okay. If I'm not allowed to repeat the vertices and the length of my path is n minus 1, okay, then what is the consequence? How many vertices will I cover? All n, because I have n minus 1 edges in the path. Right, good. All n. So since I've covered all the vertices, this is G has a Hamiltonian path. So both the directions are proved, and therefore Hamiltonian path reduces to the longest path problem. Okay. Okay, the reduction is fine, Suraj. Clear, good. Okay. Now my second claim. Okay, second claim, I'll call it claim 2.2. Okay. So remember, we want to talk about long path. We want to talk about long path, not longest path. Okay, finally. Longest path is check whether it is the longest path or not. Long path is check whether there is a path from S to T of length at least k. Check whether there is a path from S to T of length at least k. Now my claim, I'll write it here. Claim 2.2 is as follows. If long path is in P, okay, then longest path is also in P. Any idea how? It is quite straightforward. What does long path do? Given G, S, T, K, check if path from S to T of length at least k. Okay.
So yeah, we can replace say k by n. So then the long path problem will become longest path problem.
Long path problem will become longest path problem. We can not exactly. Longest path does not say whether there is a path of length n or not. It says whether there is a path of length k or not. But you are close. Okay. Goel, what do you mean by order then? Yeah, Suraj.
Sir, we can check for all values of k from
Exactly. Good. So good. Go over all k. Okay, which is go over all k prime, let's say, which is greater than equal to k. Okay, and check if k prime check if, what are we trying to decide? The longest path we are trying to decide, and using this, right? Yeah. Okay. Go over all k prime not greater than k. Sorry. Okay. Need to decide longest path using long path, right? And let's say the longest path has parameters g prime and k prime. Okay, and what we simply do is we have to find the longest path, go over all k, okay, in 1 to n minus 1, and check if GST, not even GST, go over all ST, because that longest path could be between any vertex. Okay, over all ST in the vertices. Okay, and go over all k, go over all ST, and check if GST comma k in long path. Okay, I check. What does long path say? It is at least k length. It is at least k plus 1 length, and that's how we go, right? It is at least 1 length. Keep going. It is at least there is a path of length at least 2. There is a path of length at least 3, and so on and so forth. Okay, until there exists a k s t for which there exists a k s t combination for which this GST k does not belong to long path. Okay, I'll call it k plus 1. There exists a k plus 1 value for which it is not true. Okay, that there exists a path of length at least k plus 1. Then I'm done. Then k is the answer, and then match with the parameter. okay, whether k is equal to the k given, okay, but check whether k is equal to k prime. That this is clear. Is it an exponential algo? Okay, let's see. Go over all k from 1 to n minus 1. How much time does this part take? This entire place take? This takes order n minus 1 or order n. Okay. Go over all st in Vg. G has n vertices. Go over all pairs s comma t. And what is that? This takes n choose 2 times. Every time you're choosing 2 pairs out of n. Okay. And this part, check if G is in long path. Okay. We are already assuming that long path is in P. So it runs in some n to the c time. So this part takes n to the c time. Clear? And answer is n times n choose 2 times n to the c. And what is n choose 2? This is nothing but n times n minus 1 by 2. So order n square. So which implies that max of n to the c comma n square is the running time, which is still polynomial. Is that clear, Suraj? Okay, Goel, is it clear?
Yes.
Yeah, right? Okay. So now we've shown that if long path is in P, then longest path is in P. Then longest path is in P. Now if longest path is in P, then what is in P? Hamiltonian path. Okay. Now if Hamiltonian path is in P, and Hamiltonian, remember, Hamiltonian path is NP complete. If Hamiltonian path is in P, what do we have? P equals NP. So knowing that long path is in P is a huge deal. We'll resolve the question of P equals NP, but we have not resolved the question yet, right? So it is not known whether long path is in P or not. Therefore, so the long path is in P or not, we do not know, because if it was known, then you can solve Hamiltonian cycle problem, a Hamiltonian path problem, and we are done. We can show n P equal to n. And long path is in P, short path is in P, while long path is not known. Is this clear?
Yes.
Yeah, right? Okay, good. Okay, that's done now. Okay, this I think you were able to do it, but it's okay. Okay, should I do it? I think I'll skip this one. Okay, I think this is pretty straightforward. Do you just let me know if you want to discuss this one? Click and independence.
So click can be reduced to independent set, and independent set can also be reduced to click.
Correct, right. What is the reduction?
Is there? So reduction is that in click all the maximum set of the vertices, wherein every vertex is connected to every other vertex, and getting the click of a graph is seen as getting the independent set of okay, there is a relation. So like say the getting the click of a graph is seen as getting the independent set of the inverse of the graph.
Right. Not the inverse, the complement. Complement of the graph.
Inverse, I mean complement. So wherever there is an edge, do not include the edge, and wherever
Right.
there is not an edge, include the edge.
Good. That is correct. Right. So if I have a graph G, I have a click here. Okay, and a click is simply a set of vertices where all of them have edges across each other. It's a small complete graph, in other words. Okay, and if I do a complement, that if there are edges between two vertices, I remove the edge, and if there are no edges between the two vertices, then I add the edge. Okay, so this is G, this is G bar. Then these vertices will not have any edges between them, but they'll have edges to others where they did not have. So this forms an independent set. So the sigma, okay, simply takes the G and K and then transforms it into G bar and K. That's it. That's the reduction. Suraj, is this clear? Or do you want me to discuss in depth? Clear, right? Okay. So this is the reduction. So and the other way around is also true. Given an independent set, I'll complement it and make a click, and they both reduce to each other. So we'll. This is the answer. Good. Okay. Good. And okay, this one I hope you remember. I had discussed it in depth. Okay. And right, what it talks about is the algorithm to check primality, whether a number is prime or not, and it uses the naive method of going across each number and then checking whether it divides that particular number or not. If none of them do, then it's a prime. And well says the algorithm correctly decides if n is a prime, but not a polynomial time. Exactly, it is an exponential time algorithm because it is given in binary form, right? So if the number is n, then it will be log n, and my algorithm runs in some poly n time, which is equal to exponential on log n. Good. Right. Now this is done before. Good. So I'll move on to the assignment 2. Okay. This also the question 1 of assignment 2. Any idea? So because this is also not very difficult. This is not difficult actually, if you think about it. So consider a CNF formula phi where each variable appears only as a negative literal. That is, each clause is of the form phi I1 bar, phi I2 bar, and so on. These are called negative literals. They are in the complemented form. Okay. You cannot have a positive literal. For example, xi1 is not possible because there is no complement sign. Okay, this is a positive. That was a positive literal. This is all negative literals. Each clause has negative literal. Consider the problem of deciding if such a formula is satisfiable. What can we say about this problem? Is it NP? Is it NP complete? Is it co-NP complete, and so on? Not enough information. Okay.
So the point is that if we so at the most say this formula is CNF. So if we this is same as at the most this formula maybe there in the disjunctive normal form. If we use the De Morgan here and bring this complement out of the entire thing, then the clause would be in the form of what? Then this will be in the form of what? Sum of the product of, I don't remember. But even if the formula is in the DNF, so it will not have any impact over the nature of the problem, and the problem would still remain NP complete only.
Okay. And Suraj? B. The problem is NP complete. Okay, so both of you have claimed that it is NP complete. Okay. So okay, I'll come to this then. Okay, since Goel brought about DNFs, I'll come to this. I'll do the DNF question here. Actually, I had put this in problem solving session also, but I did not get enough time that time to discuss this, and it was good that I did not discuss because it's there in the assignment questions. Okay. Okay. So I'll do this question first, then come back to that. Okay. So it says a Boolean phi formula phi, okay, is said to be in disjunctive normal form. What is said to be in disjunctive normal form if phi is consists of clauses and or of clauses where each clause is an and of literals. Consider the problem of deciding if such a formula is satisfiable, and what you can say about the problem. The problem is in P, it is in NP, and so on. Oh, okay. Yeah, Goel, you have a question? You've raised your hand.
So yeah, I would like to take my wordings back because if it is in DNF, then on the satisfiability of only one clause will make the entire Boolean expression satisfiable.
Exactly. Right. Good. Okay. Good. So now instead of CNF, I have a DNF. Okay. What is a CNF? A CNF is a Boolean expression, okay, which looks as follows. It has several clauses. Each clause is an or of ands. And x1, x2, x3 bar, let's say x4, x5 bar, and so on and so forth. This is a CNF. Now, what do we know? We already know that 3 CNF, where each clause has at most 3 variables, okay, 3 inputs, and 3 CNF satisfiability or 3 sat is NP complete. Even though it looks so innocent and simple, okay, just 3 inputs to each clause, okay, these are called clauses. 3 inputs to each clauses. It is as hard as NP complete. Okay, it is as hard as SAT, general SAT, or or CNF SAT. Okay. Now, I am writing it as disjunctive normal form because disjunctive means there is disjunction. That disjunction is another word for OR gate. Okay, conjunction is another word for AND gate. There is an OR gate at the top, and I have AND gates at the bottom. So the question is asking, what is the complexity of DNF set? What is the complexity of DNF set? That is what it's asking, right? Now, the problem is in P, the problem is NP complete. Is it co-NP complete? The given information is not enough. Okay. Now, what does it, okay, now my question is, okay, what does it take for a given formula to evaluate to 1, for a given DNF to evaluate to 1? Let's say on a certain input, my, let's say this DNF is satisfiable, okay, and this evaluates to 1. What is necessary? What can I talk about? What information can I give additionally? Let's say OR gate output at 1.
So any one clause, and this clause may comprised of, say, at the worst, may comprised of n number of the Boolean literals. So since DNF, this is the OR of the ends. So basically, I have to check a Boolean formula, which in worst case may comprised of n number of the Boolean literals. All the Boolean literals are being ended. So to evaluate whether this Boolean formula is satisfiable or not, so again this will no. So yeah. So but then the complexity of the solving a clause of a DNF again is same as the complexity of solving a CNF scheme. So yeah,
So,
this may become this seems comes out to be NP complete again.
okay. Okay. So DNF, your claim is that DNF sat is as hard as CNF sat. Okay. Now, but one question I just want to ask, a simple question is, if my OR gate outputs a one, what can I tell? Is able to output a one. At least one clause is equal to one. Right.
Yes, yes.
At least one clause is equal to one. Okay. That is one way of seeing it. Good. Now I'll ask the other way around. Okay. Let's say at least one clause is one, then my DNF will output one. Right. At least one AND clause is outputting, not out, I'll not write it as outputting anymore, I'll write it is satisfiable. There exists an input which will set it to 1. Okay. Then entire DNF phi is satisfiable. Even if one of them is satisfiable, then entire DNF is satisfiable. Okay. Now here is the strategy. I go over each clause. First this, then so on and so forth. I check whether each of them are satisfiable. Even if one of them is satisfiable, I'm done. Is that clear? Go over each clause and check satisfiability. Okay. Now what does checking for satisfiability here mean? Okay, how do I check for whether an AND clause is satisfiable? Suppose clause Ci is of the form, okay, x1 and x1 and x2 and so on till xk. So this is a particular clause, okay, and let's say there is no repetition. Okay, there is no repetition, okay, of variables. Then what is an assignment that will set Ci? Then setting x1 equals x2 equals and so on till xk equals 1 is fine, is enough, satisfies the clause. Right.
Yes.
Right. Now let's say there is a repetition. Okay, x1 and x2 and again x1 and so on till x2 and xk. This is what happens. There are repetitions. Okay. Now there are repetitions. x2 and x1. But here also I can use the same strategy. I can set all of them 1. Then setting x1 equals x2 equals and so on till xk equals 1 satisfies Ci. No problem. So as soon as I find such a clause, when going over each clause, as soon as I find such a Ci, in both the cases, I'll just blindly accept. This is my algorithm. Okay. This is case 1. This is case 2. There are repetitions. Okay. Ci has repetitions. Okay. Now, final one. Case 3. Ci contains xj as well as xj bar. Then we are sunk. Then what will happen? Say suppose Ci is something like x1 and x2 and x3 and x1 bar and so on till and xk. Okay, and now if x1 is set to 1, then x1 bar equals 0, and if x1 is set to 0, then x1 bar is set to 1, then x1 is equal to 0. So this clause is not satisfiable at all, because any assignment to x1 I give will not satisfy the clause, right? Getting it?
Yes.
Right. Ci is not satisfiable in this case. Then what do I do? Now my final algorithm is as follows. Okay. Go over each clause. Okay. And check if Ci clause Ci is of form case 1 or case 2. If yes, then accept. If no, go to next clause. Okay. If no, what does it mean? If no, then it is unsatisfiable, and you keep doing this. You go to the next clause and then check whether it is of case 1 or case 2. If no, it is of case 3 type, so it will not be satisfiable, and keep going from one clause to another and so on until, okay, if all clauses are of type case 3, then all clauses are unsatisfiable. If all clauses are satisfiable, then phi is unsatisfiable. The entire expression is unsatisfiable, and then output no. Now this, I go over each clause. How many clauses are there? Well, the size of the input. And each clause will only have n many, at most n many inputs. So this entire algorithm runs in polynomial. Getting it?
So what about the effort required to determine that all the clauses are of the form case 3? That a boolean appears as its complement.
Exactly. We only need to check whether a complement is there, and it's whether two variables and its complement are there. I mean, one variable and its complement.
So for this, how much effort is required? Because for every variable, we'll have to see the entire list.
Right.
Does it exist its complement or not? That would require the scanning of n number of the cells. And I'll have to do this for n number.
Yeah. But we can use some kind of simple strategy like a hash table, no?
Maybe. Yes,
Right.
but then polynomial times.
Yeah. Now if we are, yeah, but okay, I'll explain it anyway. Let's say here's one strategy to do it. Use something like a hash table. Okay. And so initially, so this is 1, 2, 3, and so on till n. Okay. As soon as I see xi on the first location, let's say if I see let's say xi, okay, where I is 1, okay, then I'll set it to 1. This hash table. The rest are all zeros. Then I see okay, x1, then I'll set it to 1. Then I see x2. Okay. Then I'll set that x2 to 1. Okay, let's not say x2. Let's be more interesting about it. Let's say I see x3. Then this thing I'll set it to 1. So this was 0 previously. I set it to 1. And I keep doing this. And if I see, okay, a complement later on, let's say I keep doing this and I see an x3 complement, then I look at my hash table and I'll see, oh, okay, there exists a 1 here. And here I've seen an x3 complement. Then, a variable and its complement exist here. And what you might say that what if x3 bar appears first? Well, then I'll set the hash table to store, let's say, -1 or 2. And then later I'll see that I have x3, and then I'll look at my hash table and I'll see, oh, okay, -1 is there or 2 is there, whatever the representation for the complement is. And here I have an x3, so I have a variable and its complement. Okay, and how much time will I take? I'll just take one pass. I mean through the clause. Is that clear?
Yes.
Right. Okay. But I get why you asked this question. It's good that you asked this question because one way to do it would be obviously go over. You look at x1 and then go over all n minus 1. Then look at x2, then go over all n minus 2, and x3, then all n minus 3, and remaining, and so on. But if you do that, it will take exponential time. Okay, convinced? Okay. Okay. So what is the implication finally? Therefore, DNF SAT is in P. This is why we are focusing only on CNF. Okay, good. This is why we are only focusing on CNFs. Okay, 3 CNF. We don't talk about 3 DNFs or something because DNFs is simple to solve, much easier than CNFs. Okay. Now we come back to the first question. Okay, Suraj, is it clear?
Yes.
Okay, good. Yeah, Goel, you have a question.
Yeah, so I don't exactly remember, but in discrete mathematics, there used to be some theorem which says that every pos can be converted into SOP, sum of the products can be converted into the product of the sum.
Right.
So in that sense, I guess that every CNF is in DNF and every DNF is in CNF.
Yeah. Right. Every Boolean function can be represented as a CNF also, as a DNF also. But the problem is not with the Boolean function. The problem is with the representation. When the representation is given as a DNF, it becomes extremely hard to check satisfiability. When it is a CNF, it becomes when it is the representation is a DNF, it becomes easy to check it. And if the representation of the function is a CNF, then it is incredibly difficult. If it's a 3 CNF or higher, okay, it's incredibly difficult. But the statement is still true that any CNF can be converted to a DNF, any DNF can be converted to a CNF. Now the question is, why don't we do that? Why don't we convert the given CNF to a DNF, right?
Yes, that is what my question is.
Right. So if you convert a CNF to a DNF, remember how we used to do it. We'll make a truth table, and that truth table will change all the ones to zeros and then get a DNF out of it. Yes. In the truth table, we only look at the zeros, and those positions we make a DNF. But the complexity of making an entire truth table, that is very high. You are going across all assignments, satisfying assignments. It's exponential.
Yes.
So that is not an option for us.
Yeah.
Okay?
Yeah.
Okay, good. So now, the tactic that you were using, Goel. So now with that new tactic and that information we have just now about DNF set, what should be the answer you think for this question?
Yes. So yeah. So now we have been given a formula and variant everything, every variable appears as a negative literal. So what I'll do that I'll replace, since every variable is appearing as a negative and not any individual one. So since every variable is appearing as it's negative, so I will replace it by some other variable, and which is not in negative.
Okay.
So then.
But what was your previous strategy? You had a nice strategy before, no? I remember.
Yes, so I was using De Morgan that time.
Yeah.
So I was just taking its complement, the complement of the entire thing.
Yeah.
And
Yeah.
the complement of the entire thing. So then this will become what? Then this will become. Say the complement of a DNF problem.
Correct.
And the complement of in DNF is in P. So therefore, the complement of the DNF would also be in P.
Exactly.
With P itself. So that is
Exactly.
the problem is there in P.
Exactly. Good. So now, see, Goel is Goel. The answer is that the problem is in P, right? Oh, okay. I got 0 for marking NP completed, so I think it is in P. Okay. 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 Nice answer. Okay. So the problem is in P because so I see that there is a more straightforward answer to this one. So we don't need to go through DNFs and so on. But I found it interesting when Goel talked about De Morgan's law to use De Morgan's law, but finally it ended up going to NP complete instead of P. Okay. But yeah, here is the so here was Goel's logic, okay, which I found pretty interesting actually. I had not thought about it this way. So you have a CNF only, but all the literals are actually in negative form. So x1 bar, x3 bar, x5 bar, and so on, x2 bar, x4 bar, and so on, and so on. So all are negative. Okay, they are complements. Now, the what I thought about was so my answer is just as follows: set x1 to xn, all of them as zeros. If you set all of them as zeros, then x1 bar, x2 bar, and so on, xn bar are all ones. So since the input only are negative, okay, since the input are all negative, then all clauses output 1, evaluate to 1. And so what happens? Since all clauses output 1 or clauses output 1, then entire circuit will output 1. So here is an assignment which actually satisfies the formula. Okay, if it's all negative literals, then I always have a satisfying assignment. Okay, so this is a simple answer here. So I can decide in polynomial time, in P time, because I'll just say yes blindly, because obviously there's a satisfying assignment. Okay, now, so this is clear, right? I'll just set all the variables to 0 and its complements will become 1, and then I have a satisfying assignment. So here is Goel's answer. Okay, and I found it very interesting, and that is that to convert it into a CNF with the following way. Since all of them are negative literals, I use De Morgan's law and push the gates up, push the negations upwards. Okay, what is De Morgan's law? A complement or B complement is equal to A or B whole complement. This is De Morgan's law.
A and B का whole complement.
Oh, sorry, yeah. A and B complement. Now once I push x1, x2 and so on, once I push the gates, negation gates upwards, okay, it becomes, using De Morgan's law, it becomes negation of or, negation of or, and so on till negation of ands. And now what do I do? I have an and of negations, and there is a De Morgan's law for ands also. If I have A complement and B complement, then I can convert it to an or with a negation at the top. This is another De Morgan's law. So here is exactly this form. There are negation gates and there is a AND gate. AND of negations. So this will become OR now. And there's a negation gate at the top, and then I have OR. ANDs, right? It was already ANDs. This remains ANDs. And what do I have now? I have a complement of a DNF. I have a complement of a DNF. Now I can simply check, and this is DNF sat isn't P. And I just take it, and I already saw, right? We just saw that DNF sat is in P. We'll use that algorithm of going into clause each one at a time, and if it outputs a 0, I'll negate that. Okay, I'll make it a 1 and say yes, it is satisfiable. If the DNF outputs a 1, since there is a negation here, I'll just flip the answer again. I'll say it is not satisfiable. So here also we are getting the DNF sat is decidable in Parliament. Right. Good. Yeah, Goel, you have a question? Oh, okay. It's a clap sign. I thought it was a hand, single hand sign. Okay, good. Suraj, is it clear?
Yes, sir.
Right, good. Okay. Okay. Okay, so there is one question left. Okay, we have 10 minutes, so maybe I'll only be able to discuss one question. So, would you guys want me to discuss an assignment question, or would you want me to discuss something related to space complexity, which is this week's content?
Anything which you think is beneficial, because we would be discussing some questions on the space complexity as well in the coming sessions.
Okay. Suraj? Space complexity. Okay. Okay. Goel, what had you said that time?
Yes, like I said, whatever you feel is the right within the considering the leftover time.
Okay. Okay.
And you would be discussing space complexity, if not today, then in the coming sessions.
Okay. Okay. Coming sessions will have a bit of space complexity, but I don't know whether that will be okay. I'll discuss space complexity anywhere, anyway section. Okay. This you can go over the lectures once, and you'll get this the answer to this. Okay. The answer is that both of them are NP complete, and by a chain of reductions you can tell from the lectures itself. Okay. So I'll go to space complexity then. Okay. Okay. Let's quickly look. Okay. Let's quickly get into this. Okay. So space complexity. Instead of time, we are measuring space. How do we measure space? Space is defined as the number of bits needed for computation, and usually the model is a Turing machine with separate work tape. With a separate work tape, okay, and separate work tape, and what is space now? Another way of defining space is that is the last cell used by the not the last cell. Yeah, the last cell is fine. The last cell used by the Turing machine on its work tape. Okay, and so D and what are the complexity classes? Well, D space um, Fn is all languages decidable by deterministic Turing machine using space f of n, order f of n. Okay, this many bits on the work tape, and similarly, I can define for n space also. N space f of n is the same thing, but this time I have NTM, non-deterministic Turing machine, using space order log. Okay, the order Fn. So what is NL? What is L? L stands for log space, that is D space log n. In the work tape, it uses order log n space. And what is NL? It is n space. It is non-deterministic Turing machine using logarithmic space. Okay, so this is the recap. One slight recap. We have L is contained in NL trivially. Okay, like P is contained in NP, and L versus NL problem is unknown. It is as important as the P versus NP problem. And next thing is NL is equal to co-NL. Now this is a huge result which is called the Immermann-Zelepsiny result. Theorem, Immermann-Zelepsiny theorem, which says like NP and co-NP we don't know the difference, but NL and co-NL we know. In fact, this is true for any D space, not D space, N space. Fn is equal to co-n space. So I can increase this. Okay, I can generalize this to any space bounded class. Okay, n space Fn is equal to co-n space Fn. Okay, and another thing is path. The problem of testing whether one vertex is reachable to another vertex or not is NL complete. And another thing is that NL, can we remove the non-determinism here? Can you show that L equals NL? That is first question. We are removing the non-determinism. Okay, can we remove the non-determinism? Well, you can do something close. Okay, that is NL is contained in D space log square n, and this is what is called the Savage's theorem. Can it? Okay. So I'll cut it. I'll paste it to another. Okay, good. Okay, so here's a bunch of questions. Okay, which of the following are known to be true? Stare at it, think about it, and let me know. Okay, this should be NL. Okay, Suraj says B, C, D, E, F. Okay. Well,
Yes, so for A we do not know, and for B it is by that Immerman thing, so it is true. And L is a subset of P, yes, it is true. NL is the subset of P, this is not true. Because we have a relationship in between L and NL thing. Unless both NL and NL are there in the P, I'm not sure. But even if it is NL is because if something can be done in the space of the order of Fn, then that thing can be done in the time of the order of 2 raised to the power Fn.
right.
So Nl is the subset of P. I'm not sure, but P is certainly the subset of exp. And Nl is the subset of D space of log 10 n. So yeah, deterministic space of log 10 logarithmic space, it should be the logarithmic space. So log 10 and generally the higher powers of the log are not considered to be logarithmic. So therefore, in my view, the F is also not correct. So what is correct is B, C, and then E is for sure, not sure of D.
Okay. So you said B, C.
B, C, and then E for sure.
E for sure.
Doubtful about D.
Doubtful about E.
D for and D is NL is subset
Okay,
of P.
B may be doubtful. Okay. So almost the same. F you do not agree with Suraj, and D you're not sure. Okay. Let's see one by one. Okay, quickly. We are about to lose time. Okay. So L equals NL. Okay. A is clearly not true. A is not true. Else, we solve this L versus NL question, which is again like P versus NP question. This is not true. L equals co-NL. Now again, like you guys said, this is nothing but the Immerman-Zalapsini theorem. NL equals co-NL. True. Immerman. Zalapsini. Now, C, you said L is contained in P. And like Goel said, D space Fn is contained in this D time 2 to the order Fn. And so Fn, if you take it as log n, then this is contained in 2 to the log n. And 2 to the log n is nothing but polynomial n. Okay. And so until here everyone agrees. D it is not sure, you are saying, right? Nn is contained in P. Well, it is true that it is contained in P. Okay. Why? Because firstly, the proof, yeah.
Yeah, so I think it is true if we take the Savage theorem and the solution of part number C both into consideration.
Because not Savage's theorem.
Okay. Because I thought that n space of Fn is equal to the D space of F square of n. That would again be polynomial. And then I take the 2 raised to the power of a polynomial.
So but that is polynomial, but in terms of space only. We want in terms of time. P is a time bounded class. Savage talks about D space.
Yes. So my point is that D space of log square of n. But if I take the 2 raised to the power the log square of n to log n square, but the quantity would again come out to be a polynomial only.
Are you sure?
So I think, yeah.
Let's try.
Okay.
2 raised to the log square n. What is this? 2 raised to the log n times log n. Correct.
Yes.
What is this? This is n to the log n.
Yes, but then there would be some quantity wherein this log n would be smaller than some. No.
This is not polynomial, right? Polynomial means n to the constant.
Yes.
But this is n to the some function, which is not a decreasing function.
Yeah.
So n to the log n is not polynomial.
True.
Okay, so you cannot use the same 2 to the order thing here. Okay, but this is clear, right?
Yes.
Right. But see, Savage's algorithm therefore runs in. This is what is called super polynomial time. Okay, this is super polynomial. It runs in super polynomial time, something more than polynomial time. Okay, Savage's algorithm runs in something more than polynomial time. And what is a language which is complete for NL? Path, right? How can you check path in polynomial time? Can you check path in polynomial time?
Yes, I can.
How?
So, path in polynomial time, I just need to check whether there exists a path from a vertex to the other vertex or
Right.
not. And there are many algorithms. I look into that. A
Right.
path which reachability problem. So yes, that I can solve.
So
Even I can-
what is the simplest algorithm?
So I can take transitive closure kind of a thing.
No, something even simpler. Yeah, DFS.
Yes, I can take DFS also.
Right. DFS is a very simple. It runs in linear time.
And I forgot to mention one thing that my idea of using the Savage's theorem was not correct, because Savage's theorem is valid for the values of n greater than log n. And so in this case, probably that idea that I was trying to
Savage's theorem is true for n greater than log n.
Yeah, put the value of not n is greater than log n, but then the problem size fn is greater than log n.
No. You can use it, no problem. Fn is at least it's not strictly greater than log n, right? It's not strictly greater than log n. It's at least greater than log n.
Okay.
So you can still, I mean, this is not the problem with the argument. Okay. So yeah. Anyway, you can simply use DFS. Path. Okay. Solve path using DFS. Now, as soon as you do that and you solve an NP complete problem using a P algorithm, right? Okay. Yeah. Okay. Good. So yeah. So NL is contained in P is also true. So D is correct. E is correct. Is it E? No, D. Sorry. Everything got mixed up. This is C. What is happening? A, B, C is contained in P. NL is contained in P is D. Okay. This is the answer. Sorry, what am I doing? Okay, this is the answer. Okay. So now we are nearing the end. E. Okay. P is contained in EXP. So let's see what you guys answer. Both of you said yes. P is contained in EXP. Oh no. But remember, the question is asking not that it is contained in EXP. That is trivial. Is it strictly contained in EXP? Can you tell? Why is it strictly contained in EXP? That is, there are languages in EXP that cannot be solved by a P machine. Okay? Yeah.
Yes. So, EXP, like say, the satisfiability problem is in EXP.
Well, yeah, but satisfiability problem, we don't know whether it's in P or not, no? So it's not enough to argue. Maybe satisfiability problem is in P.
Yes.
Okay, so I'll give you the answer. The answer is the time hierarchy theorem. which I think was the first lecture of this week. Okay, time hierarchy theorem. What does it say? It says d time f of n is strictly contained within d time f of n times log n. As long as your complexity class is some log n factor away, it is strictly contained. So there are languages here which are not here. Okay, so if you increase, give me more time. Okay, if you give me some more time, then I will definitely be able to compute something more, some more problems. So that is what that is the beauty of the time hierarchy theorem. Getting it?
Yes.
So now even with a log n factor, I am able to get an additional language that I can decide. If I have a gap like the gap between exp and p, then it's tremendous, right? So this is d time n to the c, and this is d time union of n to the c, whatever, and this is d time 2 to the n to the c, whatever. So this is a huge gap. Then obviously there are so many languages that exp can compute, but p cannot compute. Okay, so E is correct by time hierarchy theorem. This is clear, right, to both of you?
Yes.
Okay. Okay. Suraj also, I hope it's clear. So NL is contained in D space. Now I think the answer is straightforward. NL is contained in D space log to the 10n. It's written. So we already know that NL is contained in D space log to the 2n. So obviously it is contained in by Savage's theorem. Okay, so obviously it's contained in D space log to the 10n.
Yes.
Okay then. Yeah. Okay. So Suraj's answer was correct. It's B, C, D, E, F, and F here. Okay. Well, this is due to Savage's theorem, direct application. Okay.
Yes.
Okay. And the remaining questions maybe you can try. Maybe I'll discuss it next week. Okay. So yeah, and with that we'll end the session. So if you have any quick questions, then we can maybe quickly address, or we can call it a day. Okay.
So when will you upload these notes?
I think. It was okay in the announcement tab. There is a in the announcement part of the Soyam interface. There is this announcement that comes now that problem session has been recorded, and here you can find the notes and so on. But I can share it here in the chat also. Okay. Complexity. Okay, wait, I'll share it in the chat. So yeah, can you? Yeah, here I've sent. Okay. So in this spreadsheet, there is a Google Drive link, and in that Google Drive link, I upload the notes. Okay.
Yes. Thank you so much.
Okay. Then thank you, Goel. Okay, thank you, Suraj. Okay, thank you, Suraj. Okay, now let's all part for dinner. See you next week, same time, Tuesdays, 6 p.m. Okay.
Thank you. Good night. Bye-bye.
Okay then. Good night. Good night. Okay. Good night, Suraj.